So we've been looking at equations, specifically linear equations, but equations are really just ways for us to relate variables like x and y. Now, as we look at other kinds of equations, not just lines, not just linear equations, there are different kinds of equations that we're going to be seeing, and some of those equations are very special. Some of them are called functions. A function is a special kind of equation or relation between x and y where every single x value is corresponding to exactly one y value and no more than that. We're going to be looking at functions, but only just an introduction of functions. When you get to college algebra, you'll go into a lot more detail and really go into that definition of a function into a lot more depth. What we're going to be looking at is just a graphical representation of what would be a function versus something that's not a function. And the key to helping us identify a function graphically is something called a vertical line test. A vertical line test says that if a graph has a vertical line that is going to only touch it in one spot at a time, it's a function, where if the vertical line touches the graph at more than one point, then it's not a function. So here's an example where this graph is a circle, and if I were to take, say, a vertical line and just kind of scan over this picture, you can imagine that there are a lot of different vertical lines that are actually going to hit or touch that graph in more than one spot. So for example, if I look where x is 2, and there is a vertical line at x equals 2 that actually slices through this circle in 2 different locations, the fact that that vertical line can touch the circle more than once tells me this right here is not a function. If it only touched once, it would have been. But if there exists a vertical line that can touch it in more than one spot, this is not a function. So let's take a look at a few more examples using the vertical line test to figure out, is this stuff a function or not? In this next example, the picture that we're looking at is the graph of a parabola. Again, we want to ask, is this a function or not? And using the vertical line test, we can make that determination. So if I imagine vertical lines cutting through this parabola shape, every single vertical line I'm considering, I don't see it touching in more than one spot. So for example, back here when x is -3, if I consider a vertical line such as that, it's only touching the parabola at one point. And any given vertical line that I can consider as I'm moving from left to right, those all will only ever touch the graph at one location, at one point. And so this is an example of something that is a function. So the circle touched in 2 spots in many of the different places that I was looking at. The parabola, I'm only ever going to hit it one point at a time. So this one is a function. So next we have the graph of a cubic equation, and again we want to ask, is this the equation that's a function? So is this the graph of a function? So again, we're going to use that vertical line test to kind of scan through the image with vertical lines and ask, does a vertical line ever touch it in more than one point? So as I imagine some vertical lines here and I scan slowly across, I'm never actually seeing this touch the graph in more than one location. So just as an example, if I were to go down to where x is -1, there's an example of a vertical line. It's only touching in one location, and that would be the same case for any given vertical line that I could potentially draw for this particular example. So because it only ever touches the graph at one spot, this is again the graph of a function. So just like the parabola, this one is also a function. Let's look at another. This next graph is called an ellipse. Again, we want to ask, is this the graph of a function? So we're going to take our vertical lines and we're going to kind of scan through it and just ask, are any vertical lines going to touch it in more than one space? And just like with the circle, I'm seeing that there are vertical lines that would in fact cross through this ellipse at more than one point. So here's an example of a vertical line that would hit the ellipse in 2 different locations. So this is another example, like the circle, of a graph that is not a function. Here's an example of a graph of a square root equation. Again, we want to ask whether this is a graph of a function. So we'll take an example of a vertical line and kind of scan over this and ask, will that vertical line ever touch the graph at more than one location? And it doesn't look like it will. As an example, if I looked at the value where x is 2 and I imagine a vertical line cutting through that location, it's only ever going to touch that graph at one location. So this is another example of a function. This last graph is one of a rational equation, and rational is just a sneaky way of saying fraction. So if you always get the heebie-jeebies from fractions, this graph kind of tells you why. There's some funky stuff happening in here. It's probably hard to see on the camera, but there is a dotted line that's cutting through this place here where there's kind of a hiccup where we have one piece of the graph that jumps off and then picks back up here and extends. That vertical dotted line that we have here is what's called an asymptote, and it's basically like a force field that attracts the graph toward it. So the graph is going to get close to that force field. Same thing down here, it's getting close to it, but it's never actually going to touch it. So this is basically an off-limits magnetic force that's pulling the function or the equation toward it. So I probably just gave it away that I called this a function. Let's take a look at the vertical line test to show that this is a function. As I start on the left and continue, the only thing I'm seeing here is this bottom piece, and in that bottom piece, I'm never touching it more than once. And the same thing is happening here. The only place that might be a little bit worrisome is maybe where the graph looks as though it might be starting to get vertical, but technically it's not getting vertical. It's never going to actually be a vertical line. Remember what the arrows are telling us. These arrows say continue in the same fashion. So if we imagine kind of from this point here to get to that arrow is telling me I'm going to continue going left and up. I'm going up as I go left. And so that arrow just says go up and left. If I'm always going to be moving left as I go up, that's not going to be vertical. Same thing here. From this point as I move to the right, I'm going down as I go right. If I'm always going right as I go down, then I'm never going to be perfectly vertical. And so even though it might visually look a little bit troublesome, it is technically only touching at one point. This is a function. So that is kind of a funky example. It's a little bit difficult to see, and we have to rely not only on our eyes, which can be a little bit deceptive here, we have to rely on what we know the arrows to tell us. The arrows again say continue in this fashion. So if I'm going up and left, there's no way that I'm perfectly vertical. I'm always going a little bit one direction or the other if I'm moving left or right. It's never going to be perfectly vertical. So again, this is a rational, which looks like a fraction when you see it in the actual equation, but this is, again, a function. So now that we can identify from a graph whether something's a function or not, we want to go one step further and ask, for that particular graph, what's the domain of the graph and what is the range of the graph? The domain is going to be the interval of x values that appear in the graph as we move from the left to the right, and the range is going to be the interval of values that appear from the bottom to the top. So what I like to do for this picture, excuse me, of the circle, what I like to do is pretend that I've got a scanner, and if I'm going to be looking for the domain, which are my x values, I'm going to take a vertical scanner and I'm just going to pass that scanner from the left to the right, and I want to basically ask, as I'm scanning from the left to the right, where am I picking up a picture? So the domain is going to be, again, all of your x values. And we're going from the left to the right. And we're going to write it in interval notation as we are looking at an interval from the left to the right. So as I'm scanning from the left to the right, over on the left here, I don't have a picture. So as I scan from the left to the right, I continue on. And then once I get to that point there, where x is -2, that's when the picture begins. So my domain is going to begin back at -2. That's as far left as the picture starts. And then as I continue pushing that scanner from the left to the right, I continue to see a picture up until I reach the value x equals 4. So between -2 and 4, between the x values of -2 and +4, that's where the picture exists. Outside of those values, there is no picture. So again, domain is about the horizontal movement from the left to the right. Now, because this is interval notation, I need to include either square brackets or round parentheses, depending on whether I can equal those numbers or not. Now, because -2, for that x value, there does exist a point there on the circle, I'm going to use a square bracket to say that I can't actually go all the way to -2 and equal that number. And the same is going to go for that +4, because I can equal that number. There is a point that exists there in the picture. I'll use a square bracket. Now for the range, it's the same idea, but instead of going left to right for x values, I'm going to go bottom to top for the y values. So the range is going to be all of your y values. And as I take my scanner on the bottom, I see that there's no picture down here, but as I move up, I begin to see a picture right where that y value, that height, is -2. And I will continue raising that bar up. I'm scanning from the bottom to the top, and as I go up, I no longer see a picture once I pass 4. So 4 is the highest height at which there exists a picture. And as we saw with the domain, because there's a height achieved or a picture at the height of -2, same with the height of 4, I'm going to go ahead and use a square bracket on both of those values. So let's take a look at another example of how we can find the domain and range based on our picture. Again, domain scanning x values from left to right, and the range scanning y values from bottom to top. To find the domain and the range of this parabola, again, I'm looking at the interval of x values as I move from left to right, and the interval of y values as I move from the bottom to the top. So for the domain, we're looking at those x values. And so what I would recommend is imagining that you had a scanner that was moving from the left to the right, scanning this picture, looking for where does that graph exist. Now the domain for this particular example is a little bit tricky because these arrows are visually deceptive. They appear as though they're pointing up, and so we, in our mind, imagine, okay, this graph is going up, but we don't consider whether it's going left or right, when in fact it is. So the arrows are saying we continue in this fashion forever. They're not pointing to a direction necessarily, they're just emphasizing this continues forever. So if you imagine kind of where you hit rock bottom here at the vertex of this parabola, what's happening from there on the left side is we are going toward the left as we rise. And so we're going left and up and left and up, and while we rise steeper as we continue, we are continuing to go left and up. Likewise, on the right side, from that bottom vertex, we are going to the right and up, to the right and up. And yes, we get steeper and steeper, but that pattern of going right and up continues. That's what the arrow is telling us. So keep that in mind as we're going, that in this picture, while the arrow appears to be pointing up, this is actually going left and up forever because of the arrow. And over here, we are going to the right and up forever because of the arrow. So keeping that in mind, let's now consider the domain. The domain is asking from the left to the right, where does a picture exist? Now, as I'm going over here on the left, while I don't necessarily see a picture that far over there, the arrow is telling me I will continue to go up and left. So I continue to go left forever, which means my x values will extend all the way down to -infinity. And we've seen before that since infinity is not a number, I'm going to use a round parenthesis there to emphasize that I can't equal -infinity. Now, as I continue scanning from the left to the right, I continue to see a picture through all of this. And as I get to the right, I stop seeing a picture visually, but I know that that arrow tells me technically the picture does continue as it moves to the right and up indefinitely. And so I will continue right all the way to infinity, but again, I won't equal it because it's not actually a number. Now, as far as the range, this was again the y values. And so I'm scanning from the bottom to the top to ask, where does a picture exist? Now down here at the bottom, there is no picture, and there are no arrows telling me there's a picture down here. So as I'm scanning, I see nothing until I reach this height of -4, where y is -4 is where I begin to see a picture, and I'll continue to see a picture. According to these arrows, I'll continue up indefinitely, so my height will go all the way to infinity. I never equal infinity, but in this case I do equal that -4 height, because there does exist a point where the height extends down to -4. So there's my domain left to right and my range bottom to top for this parabola. So now as we look at the domain and the range for this cubic, again, domain is your x values from left to right, range is your y values from bottom to top. So let's look at the x values first to find our domain, and I will say that just as with the parabola, these arrows for this cubic are also deceptive. So remember that the arrows don't necessarily say I'm going there, they say this pattern continues. So let's take a look at this kind of pivot point in the center here. And from this pivot point, what's happening is as I move to the left, I'm going left and down, and yes, it drops steeper over time, but that pattern of left and down continues forever. So let me just make a note that this forever will continue going left and down. On the other hand, from this pivot point going the other direction, I'm going to the right as I rise. So I'm going up and right, and yes, I go steeper with time, but that right and up pattern continues forever. So let's keep that in mind as we consider our domain and our range. So the x values for our domain, if I imagine scanning from the left to the right for those x values, I don't actually see a tangible picture over here, but based on the arrows, I know that this will continue going to the left ad nauseum. So on the left, I continue forever all the way to -infinity. I won't equal it because it's not a number. And then as I continue from the left to the right, again, while I don't necessarily visually see a picture over here, I know that it exists because this arrow tells me it will continue to go right forever. And so this picture will continue to go right on to +infinity for the x values. Now for the range, again, we're looking at y values. This is your bottom to top, your heights. And this one's a little bit easier to see. If I imagine scanning from the bottom, I know that that arrow indicates I'm continuing down forever. So no matter how far down I start scanning, I will see a picture there. It goes on down forever, all the way down to -infinity. And as I scan from that bottom towards the top, I will never stop seeing a picture. The arrow tells me I will continue going up to +infinity. So there's my domain and my range. This basically says that the x values can be anything, any number between -infinity and infinity, and the range can be anything, any number between -infinity and infinity. So this is an interesting function because every x value will show up sometime and every y value will show up at some point on this picture. To find the domain and the range for this ellipse, again, we're going to be looking at the x values and the y values. The domain is going to be your x values. As we read from the left to the right, and this one without the arrows is a lot easier to look at. As I'm looking over on the left side here, I see no picture whatsoever, but as I scan to the right, I begin to see a picture when x is -1. And because there is a point where x is -1, I'm going to go ahead and put a square bracket to say I can include that x value. And as I continue to scan from the left to the right, I continue to see a picture up until I reach the x value of 3, at which point the picture stops. But again, because there's a point when x is 3, I will use square brackets. And so all of the values that have an x value between -1 and 3, that's the place, that's the interval over which we have a picture. We want to do the same thing for the range. This time it's the y values. And again, with the y values, we're going from the bottom to the top. So as I begin my scanner down here, I see nothing, but I will begin to see something right here at a height of -4. Because there is a point there at -4, I'll go ahead and use square brackets to show that. And as I continue scanning from the bottom to the top, I can continue to see a picture up until I reach that height of +3, where there exists a point, so I'll go ahead and put that square bracket there. So without the arrows, it's a lot easier to see where's that interval of values from left to right or from bottom to top for that domain and range. To look at the domain and the range of this square root equation, again, domain will be our x values from left to right, and range our y values from top to bottom. So let's take a look at those possible x values as we scan from left to right. Now over here, I don't see any arrows, and so there's no picture happening on the left, but there is a picture as soon as I hit that x value of -3. So the x values begin when x is -3, and I do have a point there, so I will put a square bracket to indicate I do equal -3. And then I'm going to continue from the left to the right. I continue to see a picture, and while I might not visually see a picture here, I know that that arrow indicates I'm continuing in that same fashion forever, and so my domain will continue all the way to infinity. Before we touch the range though, let's talk a little bit more about that arrow. I think it's a little more obvious that the arrow is continuing to the right because that's kind of where it looks like it's pointing, but remember, it's not about where it looks like it's pointing to, it's indicating that the pattern continues. And the pattern, if we begin from this starting point, the pattern is that I'm moving up as I move to the right. So as I continue moving to the right, I'm going to continue going up as far as what this arrow is telling me. So this is telling me to continue going up and right. It doesn't necessarily look like it's going up because it's very flat, but it technically is. The arrow says just keep doing that same thing. And so for my range, if I start at the bottom, I see no arrows going down, and so there's no picture down here. I don't see a picture until I hit that height of -4, where there does exist a point there at a height of -4. And then as I scan up, I might not visually see a picture up here, but I know that that arrow tells me I do continue to go up. And so my range, which is my y values, will continue up to infinity. Okay, so one last time as I look for the domain and the range, again, the interval from left to right, the interval from bottom to top, let's find the domain and range of this function here, and this one's going to be super fun. So again, domain is your x values and range is your y values. Let's talk x values first. This is where we go from the left to the right. Now over here, it's a little more obvious to tell this arrow is telling me I am going to continue going to the left. So I'm starting off at -infinity all the way on the left side. And then I continue. And I continue here, and it says I'm going to continue going down and right based on this arrow, but here's where I have a problem. I'm not going to go right forever and ever. I actually have to stop at some point because this here is a vertical asymptote that says you're going to get really close, but you're never going to touch. So it does continue going right in the fact that it gets closer and closer and closer and closer to that vertical asymptote, but the vertical asymptote's off limits. It technically can't be touched. And so technically, as I continue to the right, I actually stop just before that vertical asymptote, but I can't equal at that vertical asymptote. And so I have a chunk. This piece here is a chunk that goes from -infinity to almost at 0. I use a parenthesis to say I don't actually equal it. I get really close. But that's not the whole picture. That's just one piece of the puzzle. So I've scanned that left piece, and then when I hit that vertical asymptote, it's like there's some kind of an episode that happens. And then after that asymptote, I pick back up on the next piece that begins very close to 0 again, just on the other side of it. And from 0, it's going to continue going right forever to infinity. And so there's this weird hiccup here. There's two different pieces corresponding to these two pieces of the picture. Each piece comes right up against 0 in the middle, but it just technically can't touch it. Now, when I write a domain that has multiple pieces, I have to stitch them together, and for interval notation, the way we do that is we use a sort of U symbol that says union. We're going to unite these two pieces together, but they're not technically fluid and continuous. So there is a break in that picture, just as there is a break in this interval notation. I use that union to stitch those two separate pieces together. I'm going to do essentially the same thing on the range. The range is our y values going from the bottom to the top. But again, as I'm scanning, I see here's a first piece down here, and then it appears as though there's another asymptote here where there's a hiccup and a break, and then I continue back on with another piece to the puzzle. So as far down as I go all the way down to negative infinity. I'm going to come up to where the x-axis is, where the height is 0, but I'm not actually going to touch that. These arrows are hugging the x-axis just as they did the y-axis. And then the second piece picks up where the other one sort of left off, just on the other side of 0, and it will continue going all the way up to infinity. And again, if you have two pieces in your picture, you'll have two pieces to your range, and those two pieces we will again stitch together using a union symbol, which looks like a U. It just isn't technically a U because it doesn't have that tail that a real letter U might have. So it's a union symbol. And that's all there is to domain and range. Again, domain, you're scanning from the left to the right. Range, you're scanning from the bottom to the top. This was a particularly funky example. Most of them are going to be a lot easier for you in your homework, but go ahead and give them a try.